Welcome to the Plate Tectonics lecture. This portion is going to be broken up into two separate videos. In this first one, we're going to talk about a little bit about the history of plate tectonics and how this theory was developed. In the second video, we'll look more specifically at the types of plate boundaries. So, plate tectonics, the story of plate tectonics starts with continental drift. Now, this is a term coined by the man you see in the photo. This is Alfred Wegener. He is a German meteorologist who studied polar environments. He actually worked a lot in Greenland and unfortunately died there. But Alfred Wegener was a smart guy, and in 1912 he published a book. And in that, he suggested that the continents have not always been where they currently are, and that they have moved over time. And he coined this term continental drift. Now, how he got to this, right? So he had a number of lines of evidence for the continents having moved. The biggest one and the most obvious one is the fit of the continents. So if you look here, you can put all those continents back together. So North America, South America, Europe, Asia, Antarctica, Africa, and even India is tucked in there, right here. So he said at one point all of these were put together into one big supercontinent that he called Pangea. That translates to one world or all world. And this is not something that he was really unique to him. This has been suggested for actually quite a while, from the time people had done ocean-faring voyages to really see what these continents look like. They noticed that you could tuck Africa into North America and South America into Africa very nicely. But he also looked at the fossil assemblages. So if you look at where South America, Africa, India, Antarctica, and Australia are on the screen, there's a couple of big fossils that we find across large regions. So the Mesosaurus, this is a marine reptile, or I'm sorry, he's a freshwater reptile. And so he lives in lakes and rivers. We know he's freshwater based on some of the fossil evidence there. But the Mesosaurus, interestingly enough, is found in fossils of it are found in South America and Africa. They're the exact same fossils, the exact same species, so it's not like they just happen to pop up independently on both continents. So that means somehow they had to be able to move back and forth between those. Initially it was suggested that there might have been a land bridge in between South America and Africa, or that they'd swim over, but of course freshwater reptiles aren't going to last very long in that salty Atlantic Ocean. But if you stick everything back together, if you have these connected while it was alive and was able to freely move about, it works pretty nicely. Other ones, the Lystrosaurus. He is a mammal-like reptile, so he's got some mammalian traits to him, which is kind of interesting. But you can see those are found in Antarctica, India, and through sort of central, kind of south-central South Africa. And if you think about it, the current climates of those, that middle part of Africa is far removed from the climate of Antarctica currently. Now, I'm not even going to try to pronounce this one for you, but you can see he lived down along the southern edge of these. He likes it cold, though. And finally, probably the most famous of all these fossils is Glossopteris. And Glossopteris, it grew best in really cold environments, most of the time right along the edges of glaciated environments. Now, if you know anything about India, or you know anything about Australia, you will know there are no glaciers there currently. But Wegener actually found evidence that there were glaciers in these locations. Now, he's a polar guy, right? He spent a lot of time in Greenland. He knows his glaciers. And if you look, there's evidence that you can see that determines which way glaciers were moving. So they'll leave gouges in the rock when they scrape by, or they'll make streamlined shapes. So we know pretty easily kind of which direction the glaciers were moving. And India was covered in them, which seems ridiculous at this point. Southern Africa, covered in them. South America has some too. But if you take all of those, put them all back together, all those glaciers are moving from a central location, just like you'd expect. And all of them were down close to the South Pole, and much more southern environment than most of these are currently, which makes sense to have all those glaciers. Of course, not just the glacier environment, but you can see that there, but other past environments line up as well. In particular, these coal swamps and these reef deposits, and then you have salt deposits, and you have desert areas that all line up really nicely. And last but not least, mountain belts. If you go off the coast of like North and South Carolina, the rocks there are pretty much exactly like you'd find on the western coast of Africa. There's actually little pieces of the African continent there. And these go all the way up into Europe, into the Caledonian Mountains too. Plus, you have mountain belts and crusts that line up if you put South America and Africa back together as well. So Wegener looked at all this evidence and he said it's obvious they had to have been one big continent in one point. And he started telling people. And it didn't go well. Because everybody was like, hey Al. I assume they called him Al. They're like, how does it happen? How do you move a big old continent around? How do you go from everything else smushed together to them where they are now? And this little sequence diagram shows you how they did move. So here's your Pangea. Now, Wegener didn't know this at the time, but this is right around 200 million years ago. If we go forward in time, 115 million years ago, you can see the northern Atlantic is opening up a little bit. But India is still tucked in nicely there along the coast of Antarctica. 90 million years ago, you've got the southern Atlantic opened up, and you've got India starting to move further north. And between India and Eurasia is what we call the Tethys Ocean or the Tethys Sea, and you're going to see that actually be completely eaten away now. 50 million years ago, everything's starting to look a lot more familiar. You can see the Horn of Africa and the Arabian Peninsula start to develop. You can see where the Mediterranean is open at this point still. And India's trucking. 20 million years ago, you have the first forming of the Himalayas. And now where we are. We've got the Gulf of California opened up. You've got the Red Sea all opened up too. So, we know they moved, and Alfred Wegener knew they moved, but he couldn't explain how. And that's really was kind of the death of his continental drift hypothesis. He actually got quite lambasted because of it at a few conferences, which is kind of funny. Part of his problem is he was just kind of a little beyond the times and a little beyond the technology available. Because he died in 1930. He actually died in Greenland on a mission carrying food to a base of scientists in Greenland. So he died in 1930, but in the 1940s, a major event pushed world technology by leaps and bounds, and that was World War II. Honestly, it's strange to think about it, but wars can really push our technology fronts forward and really help us learn a lot more about the world around us. All right, so what they started doing is they were looking a lot into the ocean because people were a lot of military forces used submarines. And if you're looking for submarines, you got to look down into the ocean. And one of the things they started noticing is this paleomagnetism. All right, so our Earth is a great big magnet. That's why when you walk outside and you hold up a compass, it points north. Well, it actually points to polar north, not actually the North Pole. So if you're looking for Santa, you're going to need a different way to get there to him. All right. Now, so a lot of times what happens is you got iron. Iron tends to align very easily with an electric field. Now, there's a lot of rocks on Earth that have iron in them, like basalt, which happens to be on the ocean floor. So what happens is as this basalt is cooling, the crystals in it actually turn and align themselves with that magnetic field, which is pretty cool. All right, and that's so the magnetic declination is a way to describe where it's pointing to. And that changes based on kind of what your latitude is. And that's what you can see here. What they also found is at the bottom of the ocean floor are these giant ridges that are volcanoes. And there's volcanoes erupting, and as those volcanoes erupt, like you can see in the little animation, that new lava pushes the old lava out of the way. This was coined seafloor. This was coined seafloor spreading, and that term was actually used by Dr. Robert Dietz. He was a longtime professor at ASU, so there's your little bit of a local tie-in to this. So they knew that the seafloor was spreading. They finally found that, which is pretty interesting. But what they found is if you put that seafloor spreading and the paleomagnetism together, we found some really strange stuff. Right? So when you walk outside, your compass points north. And if you look in this dark gray here, right next to this volcanic ridge, everything points north, just like it's supposed to. But if you look just outside of that, like in mirror images on either side of the ridge, there are these regions where all those rocks, the minerals in the rocks, actually point south. And then they point north, and then they point south, and then they point north, and then they point south. And this was the very first indication that our North Pole, and our magnetic field as we know it here on Earth, isn't a continuous thing. It actually flip-flops. Now we know the sun does this. The sun does it on about 11-year cycles, but it was interesting to learn that the Earth did this too. And we can actually figure out when these happened. And that's one of the ways we do actually a lot of figuring out how old rocks are, is by using these geomagnetic reversals. So if you look at the paleomagnetism, so this is the historical record. Over here you have the first 4-ish million years, or at least the most recent 4 million years. Right now, this is what's called a normalchron, so this is when we're pointing north. And then when you have a subchron, that's when it points south. So you can see there's been quite a few just in the last million years or so, but if we look over here, kind of at a longer time period, it's actually flopped quite a bit. While I'm back here, one thing to note, about the oldest we have on record is about 160 million years, or at least continuous record. This is because that's about the oldest oceanic crust we have, because this up here, where 0 is right at the ridge axis in the ocean, and then it gets older and older and older as you move further and further away from that oceanic ridge. Now the other thing that they found is if you look at the rocks on the continent, so for instance, this red line, this is for North America. So if you go back in time, all the rocks of a certain age point way out here in the Pacific Ocean. And then they point over here in Europe. And then they point over here in Europe. And then over here, and then over here, until they all kind of point over here currently at the current North Pole. But Europe did the same thing. There's all sorts of locations where the North Pole was, but they're different North Poles. Same thing for Africa. And so you have two choices. Either there were 3 poles all at one time in ancient Earth, which can't happen, or they were all facing the same pole, they've just moved since then. So this is another great way, and this is one of the ways we know exactly how those continents have moved. Now, another thing you can do is you can actually go and look at the ocean floor and sample it. And what they've done is people have gone and sampled the ocean floor and looked at the ages of the rocks that are down there, that basalt that makes up the oceanic crust. And this is a map showing the ages of the ocean floor, and you can see right down the middle, particularly like here in the Atlantic Ocean, the very youngest rocks are right down the very middle of the ocean, and it gets older and older and older as you move away. The oldest rocks are right on the edges of Africa and North America, and those represent when Pangea first broke apart, which is right around 200 million years ago. You can see the mid-Atlantic ridge here is fairly narrow, really well defined. Over here, the East Pacific Rise, it's actually, that young rock is actually spread out quite a bit further, and we'll talk in class about why that is. And of course, last but not least, we can look at hotspot tracks, and we'll talk a little bit more in the next video about what a hotspot is. But basically, it's a chain of volcanoes, and it's from this mantle plume. As the plate moves over it, you get a line of volcanoes back behind it. And what we know is Kauai is some of the oldest Hawaiian volcanoes, and those rocks have been dated till somewhere between like 4-ish and 5 million years old. Oahu is a little bit closer to the current hotspot location. It's a little bit younger. Molokai is a little bit younger. Maui's even younger. And then the Big Island of Hawaii has been erupting only for the past like 700,000 years. And that's where the volcanoes are now. There's actually a youngest volcano just off of the coast of the Big Island of Hawaii, just to the southeast. And its name is Loihi. And Loihi is still erupting underwater. So what happened is all of this finally came together, and in 1960, a man named Henry Hess published a paper in which he described plate tectonics, of the Earth having this rigid lithosphere of broken plates that all move together, and he defined the different types of plate boundaries. And that's really where geology gets a start. At least geology as we know it is that 1960s paper. Now, it took a little while for people to really accept this, but basically by the end of the 60s, it was fairly well accepted that plate tectonics happened and that this explained a lot of the phenomenon we see around. All right, so here are those plates. So the plates represent the lithosphere. That's the brittle part of the crust. They're broken up into 7 large ones. The biggest of all of this is the Pacific plate. I know North American and Antarctic look oddly large, but they really aren't that big. And quite a few small plates, like the Juan de Fuca or the Cocos, they're pretty small, and all sorts of little microplates that you can't see that are tucked in between those. Now, the important part of these is where they touch, because those are called the plate boundaries, and the edges of the plates interact, and that's where you get geologic structures, where you get earthquakes, where you get volcanoes, where you get tsunamis. All sorts of exciting things happen there. So we're going to focus a lot on the plate boundaries, so the lines that separate them here versus kind of the interplate areas, but we'll talk about some of the special events that happen in between. Now, the biggest things we can look at to determine where those plate boundaries are is earthquakes. So if you look at all the earthquakes here from 1900 to 1999, you can see there's an obvious trends in here, particularly around the Pacific Ocean. But you can see that outline of the Pacific plate. You can see the Philippine plate. You can see where that Cocos plate is. You can see where the Caribbean plate is. You can even see that that ridge right down the middle of the Atlantic Ocean there that separates North America from Africa and Eurasia. You can also look at volcanoes. If we look at where all the active and recently active volcanoes are throughout the world, you can see it follows along the same general trends. Although there are locations like over here in the Himalayas that don't have many volcanoes, but do have a lot of earthquakes. So we're going to talk in the next video about why that is. Another interesting one to point out is this line down here through East Africa, all the volcanoes that are there. And you can see those tend to line up really nicely with those plate boundaries. That outline of the Pacific plate, there was that Cocos and Nazca and Caribbean plate. Alright, so just as one last little reminder, so what's actually making up those plates is the lithosphere. The lithosphere is made up of that crust in the very top part of the mantle. That's that cold, brittle, easily broken pieces. And those sort of ride on top of this soft asthenosphere that's in the lower part of the upper mantle. Alright, so now you know where the theory comes from. Next time we're going to look at exactly what happens at those different types of plate boundaries.